Today, what I am going to talk about is this proposed long-term roadmap or long-term change for the beacon chain that changes how finality works in the beacon chain, that changes how the beacon chain comes to consensus. So it's still proof of stake, but the proof of stake ends up being designed somewhat differently in such a way that it finalizes transactions much more quickly. It finalizes transactions after a single slot. And instead of using the entire validator set to finalize, it uses committees. And I'll talk about like what problems I'm trying to solve with this kind of approach. And basically, what are the advantages of doing this? What are some of the disadvantages? And just like why I think this is a path that is worth exploring. Not like this is not something that I think the Ethereum ecosystem is like needs to start putting a huge amount of like effort into thinking about immediately. So this is something that's still lower priority than the merge. So less important than the merge, less important than sharding, less important than statelessness, but still in the longer term, something that may be worth going towards. So basically, the way that the Ethereum beacon chain works today, right, is that we have this concept of a hybrid fork choice finality mechanism. So the consensus algorithm, the algorithm that the chain uses to figure out which block actually represents the head, which block kind of existing nodes and validators should follow. It's hybrid fork choice and finality, right? So it has this concept of finality. So in the same way that BFT algorithms like Tendermint have finality, but then it also has a fork choice rule, right? And the fork choice rule is LMD ghost. The finality mechanism is Casper FFG. And so LMD ghost and Casper FFG together, they're usually called Casper, right? So the way that this works is basically that once a validator proposes a block, there's a lot of attestations, these many different messages that are being made in parallel. And so after one slot, the block has hundreds of confirmations, but then that block is only finalized after 2 epochs, so after about 64 slots. Technically, it could go up to like maybe 80 or 95 slots, but it takes some time. It takes more than 10 minutes for a block to get finalized. And the thing that I'm proposing here is a kind of an alternative design that may be worth switching to in the long term, where basically instead of having this separate fork choice and finality, where a block is protected by the fork choice after one slot, and then it's protected by finality after like say 60 or 80 slots, we just have some degree of finality that a block is protected by that becomes active almost immediately. So first of all, what are the problems that we are trying to solve, right? So recently there has been this discussion and debate about MEV attacks, and specifically reorg MEV attacks. Right, so there's MEV stands for minor extractable value, and it's in proof of stake. I guess it becomes proposer extractable value, but it's the same concept. And basically, the ability of miners, validators, participants in the consensus to use custom strategies to like basically modify their clients in to process transactions differently, to act differently within the consensus, in order to just increase their revenue. And the concern basically is that like sometimes this behavior is totally okay, right? Sometimes this behavior is even quite helpful for the network, and even quite helpful for the chain's efficiency, for users' ability to make more complex and more efficient applications. But there are other forms of MEV that are clearly just completely abusive and harmful, right? And reorg MEV attacks are very much abusive and harmful. So a reorg MEV attack is basically an attack where the miner or the proposer actually instead of creating a block that builds on top of the previous block, they build a block that competes with the previous block. So I make a block on top of some other block, and then you make a block on top of the same block that I'm building on top of. And so now my block and your block are sister blocks, and your block is competing with my block. And the reason why you would want to do this is so that you can basically get fees and get MEV, get revenue, not just from the transactions that you can include in your block, but also from the transactions that you can include in, or that I already included from my block, right? So you can take my transactions and take your transactions, take all the transactions and reorder them, potentially just like you would even be able to break existing Flashbots bundles potentially. There's just a lot of very mean things that you can do if you can reorg. Now, reorging in proof of work or in Nakamoto consensus is not very difficult. Reorging in Gasper proof of stake is significantly harder, but reorging in Tendermint, which is a single slot finality system, is not possible to do unless you're willing to have like most of your validators be slashed. So basically, there was a post that I wrote with Georgios Konstantinopoulos where I have like you can see what these game charts actually mean in detail. But the core idea, right, is that in proof of work, it's easy to do a reorg. In proof of stake, the proof of stake that Ethereum is implementing, it's much harder to do that. Basically, the difference is that in Gasper, you need a lot of validators to switch to doing an attack at the same time for the attack to succeed. But in a Tendermint-like design, like you actually have even more security because it's not even possible to reorg to even one single block without getting slashed, right? So once even one single block is published and confirmed, that one single block is finalized, and so there's just is no possibility, there is no way to do to revert. So this property is extremely powerful, and basically the challenge here is, well, what if we can basically take the Ethereum beacon chain and try to get some of these benefits by making it more Tendermint-like, right? So we not copy the exact Tendermint code, definitely. So like, for example, Tendermint, I think currently does not have BLS aggregation. This would definitely have BLS aggregation. But the core concept of consensus that finalizes within a single slot, we would keep that. And like basically just use that to make it not viable to make these MEV reorg attacks. So this is the first goal, right? The first goal is to basically reduce the ability of even a majority of validators colluding with each other to cheat the network to do to attack the participants in the network profitably. So this is goal one. Goal two is to reduce attacks, harms, risks that come from flaws, like issues, problems that are already known in the combination of LMD Ghost and Casper FFG that Ethereum already used, or that the Ethereum beacon chain uses today, right? So basically, there are a number of these attacks. So there is a balance attack. There's an attack that jumps between two chains in the middle of an epoch. There's this attack on the fork choice rule, where if you have 1/3, then you can rely on like the way that attestations are processed in order to reorg one single slot. So there's just a bunch of these attacks that have been discovered recently over the last year or so, and we already have ideas for, and like very well developed ideas that can be implemented soon for how the consensus can be hardened against each of these attacks individually. But these fixes they do increase complexity, right? And I think it's clear that the fundamental combination of LMD Ghost and FFG is definitely like less elegant than, and like it's more inherently unstable than it seems to be about a year ago. And so the goal here is, well, how about instead of trying to combine together LMD Ghost and FFG and having these two very different mechanisms and trying to get them to talk to each other and agree with each other, instead of doing that, how about we just use ideas that are already well known to work, which is basically just single slot finalizing consensus, right? There's plenty of papers talking about it. There's plenty of implementations of it. It's something that everyone uses. It's a very well-established and robust concept. So let's just use it. Now, we are going to still need a fork choice for the case where more than 1/3 is offline, but it's not. But that's only an exceptional situation, right? Like it's not the case that like in every single, like even in the normal case, you have this conflict between LMD Ghost and FFG, and you even have these just inherent problems in LMD Ghost popping up. So that's goal 2. Goal 3 is to increase the efficiency and decrease the cost of running validator nodes, right? So one of the reasons why the deposit size currently has to be 32 ETH, why it has to be so high, is because we really need to have a fairly low cap on the number of validators, because there's a limit to how many validators can be safely processed. And the other problem is that the actual cost of running a node can be very volatile, right? Because it depends on how big the validator set size is, right? So basically, the bigger the validator set size, the higher the cost of running a node. And it's about a linear relationship. So right now we only have about 7 million ETH, a little bit more than 200,000 validators. The cost of running a node is fairly low. But then in the future, like what if there's 40 million ETH staking? The cost of running a node could end up being much higher, right? So the cost of running a node could easily end up being up over here. And the problem is that you have basically node operators, they have to buy hardware, design their setups with the assumption that they have to survive not just this case, but they have to also survive this case. So node running cost is high. Node running cost depends on the validator set size. In the proposal, because it's committee-based, because it's based on a randomly selected sample of validators, where the size of that committee is a fixed number, the chain does not become harder to validate if the validator set size increases, right? So there's a fairly simple maximum, and you just, whatever the validator set size is, the node running cost is going to be about the same, right? So the proposal basically just means that the cost of running a node is going to be lower, and the cost of running a node is going to be more predictable. So that's goal 3. Goal 4 is to just preserve important properties of the beacon chain as it works today, right? So the beacon chain as it works today provides a high level of economic finality. It provides this really important guarantee that once a block is finalized, it's extremely expensive to revert that block, right? Once a block is finalized, in order to revert that block, you have to be able to basically get 1/3 of your validators slashed, and that the penalty for that costs like hundreds of thousands, or right now millions, like more than 2 million ETH. So we want to preserve a high level of economic finality. We want it to continue to be expensive to attack the system and to revert finalized blocks. Another important property we want to preserve, this is a property that the beacon chain has that Tendermint does not have, and that we want to have, is the continued function and when more than 1/3 is offline, and the ability to recover in the case where more than 1/3 is offline. So when more than 1/3 of a committee is offline, we do not want the chain to just stop. We want some kind of mechanism where the chain can recover from that. So that's goal number 4. So what is this new idea that I'm proposing, right? Like, how does this work? Basically, today in the beacon chain, right, every validator participates once in every epoch, right? So in every epoch, an epoch is a 32 slots. Every single validator in the entire system has to sign one attestation. It has to participate in one round. In this design, instead, consensus is done by committees. So, and there is a committee every slot. So for example, you might think, well, in every slot, there might be, for example, 8,192 randomly selected validators. And there can be different numbers that we choose. 8192 is only slightly more expensive than or slightly more than the amount of work or the amount of validators per slot today. So it's a number that we know that we can handle. So the idea would be that consensus is done by committees, and the committees are just always this size. At any point in time, a particular committee is responsible for finalizing the next block. And the committee that is responsible does not change. It stays exactly the same until one of two things happen. The first thing is a block gets finalized, or the second thing is the committee gets inactivity leaked away, right? So what that means is that if the currently there is one committee, like we'll call it like committee A, and that one committee finalizes a block, then after that, the committee can switch to committee B. If more than 1/3 of committee A drops offline, then the inactivity leak starts. And the inactivity leak is exactly like, or very similar to how inactivity leaks work today, right? So the deposits of every validator who's not participating decrease until eventually the deposits of every validator who is participating become more than 2/3 of the remaining validator set, and then it finalizes again, and that's when you can switch committees. So consensus is done by committees, and either a block gets finalized or the committee gets inactivity leaked away. This is the only way that committees change. So this is just a diagram showing an example of how this might work. So basically, like let's say we start off that here we have a block A, and there's a committee that's responsible for finalizing A, and the committee runs a consensus algorithm. The committee algorithm, the consensus algorithm, then we'll say it agrees on A and it finalizes A. Then after that, it's there's the next block, and there's a block B. And because consensus succeeded, the validator set changes, and so there's a new committee, and the new committee tries to come to consensus on B. Now, we'll say to make the example more interesting, let's say that this committee fails, right? Let's say the network is not working well, and let's say B does not get finalized, right? But let's say block B wins the fork choice roll. So now what happens is in block C, there's a validator set. Now there is an inactivity leak, and B does end up, like the validator set does end up a little bit different, and it tries finalizing B again, and it maybe succeeds, it maybe fails. And let's say the network is being inefficient right now, and so consensus fails again. Now let's say there's a block D. Now, because the network is not efficient, D does not even notice C. D instead builds on B. But the validators, they still come to consensus. They're still trying to come to consensus on the same block B. So the validator set of D comes to consensus on B, and they let's say they come to consensus successfully, and so finally they succeed. And like this might be because, well, the validators, like there's an activity leak, so the validator set, or at least the composition, the balances of the validator set are already changed. So maybe like the validators that were offline over here, they have less, their deposits are smaller. The validators that were acting correctly, their deposits are the same. And so the validators that were acting correctly, they're now up to 2/3, so they can finalize B correctly. And so now you go up to the next validator set, and then the next validator set is now trying to finalize E, and E builds on top of D, right? So basically, during every slot, the committee just keeps trying to finalize. And during when you have this longer period when you do not have consensus, then you have a fork choice rule, right? And so sometimes, like the fork choice rule decides, like, is C the head, is B the head, is D the head? Even over here, like when the committee decides to finalize E, it actually checks that E builds on top of the head, right? So you have a fork choice rule. You also have this consensus mechanism, and the fork choice rule just always runs as it does today. But the consensus mechanism, instead of working every epoch, it actually tries to finalize every single slot. So this is roughly how this would work, right? Now, for the consensus algorithm, there's two options. One option is to try to copy Tendermint as close as we can. The other option is to start with Casper FFG. So start with Casper as it exists today, but instead of having Casper FFG today, where an epoch lasts for 32 slots, you would have a Casper FFG where an epoch lasts for 1 slot. And for safety reasons, you actually have to have the validator set, like say between this and this, instead of changing completely, it would only change by 1/4, right? So these are basically the two options that I think we have. There's some interesting trade-offs between them, but I think ultimately either one of the two can work. So why is this safe, right? The reason why this is safe is because that in order for two conflicting blocks to get finalized, they're basically, like, if you have two conflicting blocks that get finalized, then there has to be some first point at which two conflicting blocks get finalized, right? Like you have two chains that, like, one chain diverges, one chain splits up into two chains. There needs to be some first block on the left chain and some first block on the right chain that get finalized. For both of those blocks to get finalized, because we know that this is how consensus algorithms work, you need either 1/3 to be slashed on both sides, or on the more recent side, so on the side that finalized later, you need to have a very large inactivity leak, right? So you need to have one of these two things to happen. And the reason why this is true is the same in the committees in this version of consensus as it is in the Casper FFG as it exists today. So exact same logic, except instead of applying to the whole validator set, it applies to a committee. But like basically the first time you have the double finalization, the committee finalizing on the left and the committee finalizing on the right will be the same. And so like you just have to have this slashing happen in both cases. If a committee goes offline, or if more than 1/3 of a committee goes offline, the possibility of an inactivity leak allows recovery. And then if a committee or 51% of the validators in a committee start censoring, then the community can do a user-activated soft fork and it can recover from the censorship, right? It can basically just go off and finalize a minority chain. So basically, it's safe for the same reasons why regular or the current version of Casper FFG, where everyone is validating in every round, is safe. Now, one important nuance here, right? This is extremely important, is the fact that the committee does not change until either it leaks or something gets finalized, right? Now, this is really important because it means that you're not going to be able to have a situation where like, oh, well, you get double finalization, you have a different block finalized on the left and a different block finalized on the right because they're finalized by two different committees. Like, no, in order for there to even be two different committees, you have to have already had a finalized block on the left and a finalized block on the right that both use the same committee. And for that to actually happen, well, you need 1/3 to get slashed, or you need an inactivity leak, right? So this is the core idea. One interesting extension is multi-confirmations, right? So basically the idea is that what I call the dynasty N committee, right? Dynasty meaning like the number of finalizations that happened. The committee for dynasty N is chosen based on data that was already known in dynasty N-50, right? So basically, like, if the data that the blockchain has today, or that the blockchain has right now, will only be used to choose committees after 50 confirmations, right? So after 50 rounds of this consensus. The goal of this is that if you have two conflicting chains, then for the committees to start to diverge, you don't just need one committee to double finalize. You don't just need one committee to finalize two conflicting blocks and get slashed. You actually need 50 consecutive committees to finalize or to confirm two conflicting blocks and to get slashed on two conflicting blocks, right? So basically, instead of requiring like one finalization or one of these round of consensus to consider a block finalized, you require 50 rounds of consensus to consider a block finalized. And then you do this trick where the committee is based on data from Dynasty N-50, so from 50 rounds of successful rounds of consensus before. And this means that you actually do have the security of 50 consecutive committees, 50 committees coming one after the other, actually adding on top of each other. So a lot of nice properties. So how does this affect cost of attack, right? So we really care about cost of attack. One of the really nice properties of the beacon chain as it works today is that if you want to revert a finalized block, you have to slash 1/3 of the validator set, right? And that costs the attacker like over 1 million ETH. It's extremely expensive. So we have a chart here, right? Basically, if you have different deposit sizes, different committee sizes, different committee look-aheads, so like this a number instead of 50, like what you actually set that number to. And one column is the amount of ETH needed to break one single committee, and here is the amount of ETH needed to break finality, right? So the number on the right is the amount of ETH that an attacker needs to be willing to burn to revert a block that has been fully finalized. And this is an extreme amount, more than 1 million ETH, completely unrealistic, right? This is what the attacker needs to break one single confirmation. So to get, it's a 1/3 of one single committee. Basically, if the attacker is willing to burn this, the smaller amount of ETH, the ETH needed to break one single confirmation, they can revert a single finalized slot, they can prevent finality for 2 weeks, and they can censor and they can force a user-activated soft fork to stop the attacker. So the attacker could do some pretty mean things with, depending on the parameters, between 3,000 and 200,000 ETH. So it's a good argument to set these parameters to be on the high side. So that's one thing that they can do. If the attacker is willing to actually burn the amounts on the right, then the attacker can do a lot, even more crazy things. Now, notice that all of these attacks, like these numbers are just the cost, right? These numbers are the amount that the attacker loses from being slashed. The amount of ETH the attacker needs, or the amount of validators the attacker needs to control is still the attacker needs to control close to 50% of the entire validator set, because the attacker, like every committee is randomly sampled, right? And to get more than 50% of a randomly sampled committee, you have to have close to 50% of the total validator set. So the budget is still very high. The amount of validators the attacker needs to control is still very high. The cost is lower, but I claim that the cost being lower is okay, because even in the current beacon chain, there's a lot of these low-cost, low-grade attacks, attacks that do not cost a huge amount, that also do not cause a huge amount of pain, but that still cause a pretty large amount of pain. So persistent, extreme, or hostile MEV extraction, griefing attacks, mild censorship attacks. There's all of these attacks that an attacker can already do if they have 50%, where these attacks are low cost and they're non-uniquely attributable, which means that you cannot like easily detect in a way that can convince everyone exactly which nodes were responsible for participating in the attack, right? So basically, if an attacker has access to controlling half the validator set, and the attacker is willing to burn 100,000 ETH, there's already a lot of very extreme things that the attacker can do. And so I would argue that going to like this committee-based model of consensus is actually like it only it does add like one new opportunity, but to attack, but the one opportunity is not even cheaper than opportunities that already exist. So benefits for validators from this design: constant node running load. So basically, instead of the the computational cost of verifying the beacon chain being variable. It like instead of it depending on the number of validators, it's a constant. It's just the size of the committee. You could actually have very quick withdrawals in some cases, right? Because most validators are inactive most of the time. While a validator is inactive, it turns out it's actually completely safe for them to withdraw. Also, a simpler code base from not having this kind of complex combination of LMD Ghost and epochs and slots. Just the code base can be simpler, and this means less software risk for validators and less software risk for users. So how do we get there, right? So for now, mostly wait, right? This is a long-term idea. This is an idea that like I'm throwing out there early, but I expect to be implemented after the merge, after sharding, after stateless clients. So not soon. There's the merges and sharding are more important and more urgent problems. For now, ongoing thinking, ongoing review. Check, does this path really make sense? And how does this path compare to CBC, right? Like if you look at the Ethereum roadmap that I published on Twitter, I think in December last year, the roadmap for long-term beacon chain evolution talked about CBC. This would be a replacement for CBC, right? It would be an alternative that has very different properties to a CBC, but properties that I think could be better, right? But are those properties actually better? Like actually do this analysis, and then once there's some more analysis, a more detailed specification and a more detailed test implementation. So that's it, and this is where we are now. So this is basically just an alternative idea for long-term evolution of the beacon chain, which is something that we wanted to do already, right? Making some modifications and fine-tuning and refining the beacon chain consensus has been something that was part of the plan since the beginning. And this is just a different way to do it. And it's a plan that at least I think deserves some consideration. It satisfies some goals that I think a lot of people care about. And for now, it's just something that's worth thinking about, and something that's just worth doing some more research and some more exploration into. Thank you.